This is the open source multimeter that I've been working on for a couple of years now. And in this video, I'm going to go over every part of it and roughly how I arrived at the design of it. The basic concepts will be very similar to other commercial multimeters, and a few of the circuits used in it are taken verbatim from other designs. But there are some differences for sure, if you're just more interested in how multimeters work in general rather than this particular project. This video won't be a complete technical dive into every single aspect. It's a little abbreviated, but well, you could see the runtime. Some things had to be skipped, and this video is a little rough around the edges just to get it out before next year and in under 6 hours. I'll start with an overview of where the project is now before we get into anything technical. Feel free to skip ahead if you're just looking for how multimeters generally work and not the HydraMeter project specifically. The design I'll be going through is somewhere around the current state of the project. I've left this as sort of a revision 1.0, and I'm moving to a full revision 2.0 now. So the current design is somewhere in between, and I'm planning to put out some videos and updates more regularly as the design evolves and I get closer to that 2.0 mark. I've made and have started testing some development boards, mainly these, which have two completely separate voltage front-end designs, one similar to the 1.0 and one that I'd like to move to for the Rev 2, and some new protection circuits for the ohms range. Thank you to PCBWay for sponsoring the boards in this project. These and the original meter boards were made by them, and they've been great. I've been getting most of my boards made by PCBWay for years now, and I'm happy to recommend them. I'm in the process of testing these front ends now, most critically their DC accuracy, but also their AC performance. I've finally bought a modern digital oscilloscope just for this, and you'll hear some of my thoughts on that later. A big chunk of the meantime has also been working on overload testing with this thing. Yes, that says kilovolts, and it's full of big capacitors, and coincidentally is probably how I will die. But worth it to almost make these things vaguely resemble a competent multimeter. Also, huge thank you to everyone who filled out the survey. I think that gave a good gauge on more than just my own narrow slice of what would be interesting here, and a desire for a rotary range switch was a big chunk of that, so that is on the menu, though I've been focusing mostly on circuitry so far. Another big one is the basic oscilloscope or graphing functions, which I haven't touched yet, but that's a software update, so at some point here I'll just program until like 4 a.m. and get that working too. Alright, so we're making a multimeter, a digital multimeter, and the main function is to measure voltage on its input, convert that into a digital signal, then display that. And an ADC takes a voltage and converts it into a digital signal. Cool, that part was easy. So a multimeter is basically just a fancy ADC and a display, right? Yes and no. It is definitely the core part of the whole shebang, but the process and parts around it end up being most of the work in the design and building of one. For one, we've also got to measure current and resistance. Those also end up coming down to measuring a voltage across something, but require additional circuitry to convert those values, the current or resistance, into a voltage measurement. Also, we want the display to detach, so we need a few more things between the digitized signal and the display, namely a pair of microcontrollers, one for the ADC and one for the display, and radios for each. When it's not wireless, they've also got to be able to talk to each other somehow, so something for that. Also, us dumb, non-electronic humans have to be able to communicate what we want to know to this thing somehow, so we need some kind of input to switch modes. And this is essentially how this is made up. Some front-end circuitry for each of the functions, an ADC, microcontroller, user interface, communications, radios, another micro, and display. If we didn't do the wireless display, we could cut out the communications, radios, and second microcontroller. So, one of the first problems we run into with using an ADC in practice for this application is that we're not just measuring positive voltages. In fact, we want to measure both positive and negative voltages with a similar accuracy and range. Just hooking up an ADC to a microcontroller, we're measuring relative to 0 volts here. And if we run our ADC at 3.3 volts, we can only measure 0 to 3.3 volts. There's a few different ways to go from here. The most straightforward, and the one I see a lot with similar projects, is to just use a negative supply. We use something like a charge pump here, which creates a negative voltage, say negative 3.3 volts, and we find an ADC that can accept that voltage range, so negative 3.3 to positive 3.3, and then either directly outputs or we add some level translation to get it up into only this to our microcontroller that only has a positive supply. And boom, we can measure above and below 0 volts at our input. This can and does work, but charge pumps are pretty noisy, and this really limits our ADC options. Not really something we want here, as it's going to be expensive and set most of the performance of this meter. We want to get the most effective ADC we can find at a decent cost. So this works, but it has some problems, and in ye olden days, this is exactly how you do it. You probably wouldn't use a charge pump, just a power supply with a negative rail, but higher voltage parts are more common, so effectively this is what you do. Another option that doesn't require either of those is to use a differential ADC, which most good and high resolution ones are. This has both a positive and a negative input, and the ADC measures the difference between the two rather than the absolute level of either. If we set up some amplifiers so that the negative goes up for a negative input and the positive goes up for a positive input, and vice versa. So for a positive input, the negative goes down. So we have amplifiers with a gain of -1 to the negative and +1 to the positive. Then, even though we've got a strictly positive supply voltages, everything's above 0 volt, we will get a negative differential voltage between these two for a negative input. So if we feed a negative input here, it'll go into our negative amplifier and so the negative input on our ADC will go up and the positive input will go down. So we end up with the negative above the positive, and so we have a negative reading out of the ADC. And for a positive voltage, it works as you'd expect. The positive goes up and the negative goes down, and so we get a positive output. There's two things with this. One is that we have to actually make this amplifier, which it's not too tough, but could introduce some accuracy or nonlinearity issues. And we've sort of hidden something significant in here, which is that to make this work, these have to start in the middle of the supply. So for a 3.3 volt supply at about 1.65 volts. You could make it work differently, but that ends up being more difficult rather than simpler. So what if instead of having both of the inputs move up and down when you have a voltage input, what if we kept the negative input, what if we kept the negative input at a constant voltage in the middle of the supply and had the positive input go above and below it? Something like this. Well, that would neatly solve our problem that would mostly solve our problem. So for with this configuration, we do have to shift our positive input up a little bit so that when Vin is at 0, the positive input is at half of our rail voltage. So in this case, a resistor divider up to the positive rail gets us where we're going. So for a 0 volt input, we have a differential between the two of 0 volts because they're both at 1.65. For a negative input, for an input of negative 3.3 volts, we have a resistor divider from 3.3 to negative 3.3, so it ends up at 0. And so we have a negative differential across our ADC. And for a positive supply, this just ends up at positive 3.3 volts and we get a positive output. So this mostly works, but we now have a resistor divider going up to a positive rail, so our ultimate accuracy depends on how accurate we can maintain this rail, and that's, again, not impossible, but can introduce some problems. One nice thing with doing a handheld meter like this is that the whole thing is floating. It's battery powered, it's separate from everything else, so there's nothing that says that our ground input and our 0 volt supply have to be at the same potential. We can instead connect our ground input to some other voltage, and then our voltage input will be relative to that, and we won't draw any current through our ground. So if we set it up something like this with our negative input tied to that intermediate voltage, and then our positive just goes straight through to our ADC, then this turns out to work. We can see for 0 volts across it, we have 0 volts across our ADC. For a negative voltage, our negative terminal is already at a positive voltage. It's above 0 volts. So relative to that higher voltage, we're only a little bit below and we stay above ground. We do have to, be careful about our range here to make sure that we're not going outside of that 0 to 3.3 volt range. But as long as we do that, we can measure positive and negative input voltages without any problems. So now in practice, we don't want to just use a direct resistor divider here, because for this simple version of it, this works fine. But once we're putting any current through our negative supply rail here, or negative ADC input here, then it's going to get thrown off a little bit. It's going to throw off because we're just using an unbuffered resistor divider there. So we add a op amp onto that buffers that output and some noise filtering. And now from here forward in all of these drawings, anytime you see this, our ground symbol like this is actually indicating halfway between our two supplies. So this is for a 3.3 volt rail, this is at 1.65 volts above 0 volts. But this is our sort of common reference, or ground, for that everything is relative to. So all of our measurements, instead of being relative to the 0 volt input here, are actually relative to this point in the circuit. And so this is effectively how we structure everything. So we've got this is sort of implied to exist somewhere off the page in all future diagrams. And then this is how our ADC and microcontroller and voltage rails are set up. So with that context, we'll move on to how we actually measure our inputs. We'll start with the current because it's the simplest. So the simplest way to measure current is just to use a simple shunt resistor. Ohm's law, any current that goes through our shunt turns into a voltage, which we can measure with our ADC. And this is exactly what we do. The high current input, especially the amps range, is literally just a resistance between our input and our ground terminal. Now, there's a little bit more complexity in that we're using a very, very small resistance here, about 5 milliohms on this. So something like a copper trace will have an appreciable fraction of that amount of resistance, even if it's fairly wide. And we don't want our copper trace to be part of that shunt resistance because it will have drift over temperature and possibly over time. And we want to rely on just the resistance of that resistor. So we use a 4-wire thing. So we split off our measurement terminals right at the edge, right at the terminals of that resistor, and have those go back to our ADC. Also context, given what we talked about a second ago with the grounding, is that our ground for all of our sensitive electronics is actually derived from the negative terminal of this resistor, or the ground terminal of this resistor, rather than going straight to our ground input jack. So in this case, this is the input jack here. It goes directly to this resistor. Anything high current, we'll get to fault currents at some point much later on, will flow in this section of the trace. And then after it comes out of here is when it connects to the ground that we're using for everything else, that we're measuring everything relative to. So the milliamps and microamps can get a little bit more complicated. So because for amps, we want a whole separate circuit because we've got all this stuff. We've got a much higher current fuse and very, very low resistance. We don't want to be switching anything in and out of this range. So that is why most multimeters have 2 separate current input jacks, a high current one for about 10 amps and then a separate one for milliamps and microamps. And this meter is no different. For the milliamps and microamps, we can do some ranging there, and that adds a little bit of complexity, but it's still effectively a pair of shunt resistors. So we have one shunt resistor here, which is a higher value, say 100 ohms, and one here, which is a higher value than this shunt, but lower than this one. So somewhere, in this case, I've picked 0.33 ohms. So this is the resistor for milliamps, and this is the resistor for microamps. So when it's set up in the microamp range, which is what's shown here, we have a switch here that's open across this resistor. So we're flowing our current through both of them in series, and then we're measuring our voltage from, as always, from our ground to the positive side of this resistor here. So because these two are connected directly in series, we don't have to worry about leakages or anything through our switches or losses in the switches, which is nice. And again, much like with our high current range, we're just measuring the voltage across there, and that divided by the resistance gives us our current. So we have a couple of switches here, one to set which input is going to the ADC, and then this one to bypass this resistor for the milliamp range, which is this configuration. So when we want to measure milliamps, we don't want the additional voltage drop of our higher value resistor, our 100 ohm resistor. So we just bypass that with a switch. And importantly, we switch where our ADC is reading from. We read directly across this resistor again, instead of from the same point. In theory, with a nice, on paper schematic, it would be fine to just read from this point in the circuit as well, because we've got a switch here, there should be no voltage drop there. So we should have the same value either way. But in any real circuit, this switch is going to have some resistance. And importantly, something like contact resistance can be very variable, both over time and just from one switch to the next. So to get around that, we instead tap off the voltage directly on the other side of this. And because these switches are drawing very little current through them, their resistance doesn't really matter that much. It shouldn't introduce too much of a voltage error. And so this is how we implement the milliamps and microamps readings. And here's some quick math on how I arrived at the different values for our shunt resistors. So one of the big things we want to minimize in our current range is the amount of voltage that drops from the input to the output. As we're, pushing our current through the meter, we have to measure a voltage across there. In theory, we could do Hall effect or something like that, but we're not doing that for this. So we want to keep that voltage down, preferably somewhere in the range of 100 millivolts or so. We could go lower, we could go higher. I wanted to have it somewhere around here. So for the 10 amp range, we do also have to worry about the power dissipated in that resistor. If we had, say, 100 millivolts at 10 amps, that's a full watt being dissipated in that shunt. So we want to keep that down. So in this case, I set the burden voltage at 10 amps to 50 millivolts, which times 10 amps is 500 milliwatts, which is still appreciable, but should be able to be handled by the resistors we're using. And then for the other ranges, that's not as much of a concern. So we just set the burden voltages to be somewhere around 0.1 volts. In the case of microamps, it's exact. In milliamps, it's close, but the exact value there doesn't matter that much. We're not often going to be operating at that full burden or that full range output. And that's pretty much all there is to the current front end, at least as far as the measurements go. We'll get to protection later on. The primary function of a multimeter is, of course, voltage measurement. Heck, we often even call them voltmeters. The basic way this works is that we have an ADC, and that converts our analog input into a digital signal, and boom, we're done. Right up until we're measuring something at a range outside the input range of the ADC, or we don't want to load the circuit with parasitics from the ADC, so like most of the time. The basic way that we make our analog front end for this is a voltage divider. So we take in a high voltage here and run it through a resistor divider to get it down into the range that we want, and boom, we're done. Again, this works great right up until we want to measure different ranges of voltage. Now, hypothetically, we could have a divider with a really high ratio, like say 1,000 to 1, and then just run it through a variable gain amplifier and sort of boost it back up into the range that our ADC can measure. In practice, this doesn't really work though. The errors and noise will be amplified as well, so our meter will be the least precise and accurate at these low voltages, which is often where we need it to be the most precise. So instead, we need to make this resistor divider ratio itself adjustable, preferably digitally from a microcontroller to do auto ranging. There's a number of different ways to do that, but none are really perfect, and I went through a few iterations on this design, and the first were not great. The first idea I had was to use a stack of resistors like this, and then switch between different points on this stack to get different ranges. And this could work if the switch could tolerate the full voltage range we want to go over. So for something like a manual ranging meter, this might be viable. But most of the digital switches I could find couldn't tolerate, up to say hundreds of volts and also have extremely low leakages, because any current that leaks into or out of this resistor ladder here is going to throw off our measurement. So it's not impossible, but not really viable for this project. The next way we can do it is to have a single resistor input and then switch the resistors to ground. This has the advantage of keeping this switch at a low voltage node at all times, so we can use a more common digital switch while still getting these different ratios. The downside to this is that we have a variable impedance coming through this divider. So our resistance from V in to ground, which is what our circuit's going to be loaded by, will change as we change these resistors. Now, the final design I used for this project was a slight variation on this, where the switch is on the ground side. So this has the advantage that this switch is always sitting right at ground potential. And the common node here, which tends to be a little bit leakier, can be put on the ground node where it's not causing any problems. So this works and is how it was built for this meter, but after implementing that, and in the next versions of this, I'm moving to a slightly different topology, which has a few advantages over this. Principally, that this input resistance doesn't change between different ranges. So a problem that this topology has is that the input resistance changes significantly as we change the range. Ideally, we'd like this to be a constant 10 mega ohm input impedance. This is usually not enough to load most circuits, but beyond that, it's sort of just the standard. And we like standards. I like standards. Now, obviously, if we just have a 10 mega ohm resistor going to ground, we can't really measure anything, and we need to do that. I want to measure things. One thing we can change from this circuit is that we can disconnect the resistor from ground and then drive that end to ground through some other circuitry, like this. As long as this point stays at this same voltage, it doesn't matter if it's connected directly or not. It'll act like there's just a straight wire going down to ground. The observant viewer will remember a circuit that does exactly that, keeping a point at ground while outputting something relevant to the input voltage, which is the inverting amplifier. Remember that an op-amp will drive its output such that its two inputs are at the same voltage. So if we connect the non-inverting input to ground, then our inverting input will be driven to the same voltage, which creates this sort of virtual ground, which always sits at this same ground potential, even though it's not directly connected. This means that our input impedance will always look like a straight 10 mega ohm resistor going to ground, but our output voltage here will change in proportion to our input voltage. And with a gain, or more accurately in this case, an attenuation, which is set by the ratio of these two resistors without influencing this input impedance at all. Ranging can be done in a similar way to the non-inverting voltage divider with a switch on these feedback resistors. These can be used to set the gain for the amplifier to less than 1, even an attenuation of several orders of magnitude, and everything stays at a low voltage. Remember, this point always stays at ground. So our high voltage is only present at Vn here, which is on the other side of this resistor. And so that means we're dropping our entire input voltage across this. And so for this reason, you'll often see this resistor broken up into several smaller lower value resistors in series, so that we don't need a huge, expensive, high power, high voltage resistor. And this is exactly what we do. Now, it might be a little bit confusing how it looks like this point looks like a wire to ground, where the current kind of flows through after it gets through this resistor. Because remember, our inputs to an op-amp here don't source or sink any current. In fact, the leakage on the op-amps we're using here is just a few picoamps. So the answer is that it flows around this loop. It flows around this loop back into the output of the op-amp, or you could think about it as coming out of the output of the op-amp, flowing through and then out of the input. but it flows into the output of the op amp up to one of the rails, whether it's pushing up or pulling down, flows through that rail and then back through our rail splitter over here that generates our ground, goes through there and then back out the ground terminal. So it goes in through our VN, around our loop, in, up to the rail, out of the rail, and then out of ground. This does make things significantly more complicated, especially for higher frequency AC signals. We can start to have some weirdness in this feedback loop. And if we exceed the bandwidth of the op amp, then we can get some weird response or ringing or a number of other effects. To understand those, we've got to look at how these work over frequency as well. These two topologies work great for DC. However, we don't just want to measure really stable DC voltages. We also want to measure AC or noisy DC, and small parasitic capacitances in the op amps and ADC and other components will start to mess with this. They'll start to cause problems when resistances are well into the mega ohms like this. This inverting op amp won't even be stable. Testing it without a feedback capacitor, there were enough parasitics in the rest of the circuit that this oscillated with no input or even a shorted input. It put out a couple of 100 kilohertz wave. To deal with this, we use this one weird trick that the test equipment companies don't want you to know, which is the capacitive divider. It turns out that capacitors can form dividers just like resistors, and they'll pass AC happily without changing the DC characteristics of the circuit. If we match the ratios of resistors and capacitors, these are both set up for a 10-to-1 attenuation, then this will act like a perfectly normal divider, but will decrease its impedance at higher frequencies to compensate for any stray or parasitic capacitances around these nodes. As long as these capacitors are much larger than any parasitics, then this ratio should be maintained, and we'll get a nicely attenuated version of the input at the output. So we put this idea back into our front-end designs, a small capacitor in parallel with each resistor, and this will pass the input to the output even at higher frequencies. For the inverting version, that is if and only if we have an op amp with infinite bandwidth, which we don't. We live in this annoying place called reality, which doesn't have those. So somewhere in the hundreds of kilohertz with the particular op amp I'm using here, our op amp will start to fall behind. Slowly at first, but if we're not careful, at some point it actually kind of comes all the way around and starts oscillating or ringing. If you look at the Bode plot, you'll see that it actually amplifies at some point here. This happens at a fairly high frequency though, and we run into another problem well before that, which is the sample rate. Our ADC can only sample up to a couple of 100 kilohertz, and if we have an input bandwidth above half of that, the Nyquist rate, then we will alias higher frequencies down into our measurements. Now, we're not really doing frequency domain analysis, so that doesn't matter that much, but that means higher frequency noise will get through this front end and be picked up by the ADC, and even digital filtering might not be able to take it out. It might show up in the digital data as a lower frequency, and we might want to measure those lower frequencies. Both of these are solved by limiting the analog bandwidth of this front end, adding some filtering. It might seem like a good idea to add this in the feedback loop for the inverting version, make this a second order filter, but that ends up being more difficult than it might seem and doesn't really help us with the limiting factor here being the bandwidth of the op amp. And in any case, this filter doesn't need to be that strong. We only need a couple of kilohertz pass band, and there's no hard cutoff for the cutoff band here. We just need to knock down our noise a little bit at these higher frequencies. So we split our input resistor again, adding a 1 kilo ohm resistor up front and using a part that we'll need later anyway, an MOV. These have some significant parasitic capacitance of their own, but in this case, we can use that for our filter. This makes a simple RC filter before the input. We set this up to knock down our higher frequencies, and this doesn't really have to interact with the feedback loop for our op amp at all. It just sort of takes everything off before it even gets in. And since the 1 kilo ohm resistor here is 1/10,000th the value of our main input resistor here, the rest of the circuit really doesn't care. To get a little more control and higher attenuation at low frequencies though, we'll also add a resistor in series with the capacitor going in parallel with our input resistor. By carefully picking values, we can sort of override that capacitor at higher frequencies, forming a low pass, but with greater control over the values and overall impedance than this first stage. The parasitic capacitance in an MOV isn't necessarily very accurate or very constant. In theory, it should be possible to just make this a single stage, but this ends up working out well, so this is how we're doing it. That's pretty much everything we need to know for the voltage front end. Moving on to the resistance measurement, there's a little bit more design space. We're trying to measure an unknown resistance, and unlike voltage, there's no direct way to do this. We have to use Ohm's law and compute it from a voltage and a current. So that means a few things. We have to supply power to the resistor and measure both the voltage and the current going through it. Just to make things more fun, I also included a requirement of my own to allow this to supply at least 4 or 5 volts, preferably even higher, for measuring things like the voltage drop of LEDs with the same circuitry. We're also measuring over many orders of magnitude, single-digit ohms up to about 10 mega ohms. That's 7 orders of magnitude we have to cover here. One of the first key ideas with this was tapping off an additional output from the voltage jack that we supply current through, rather than trying to pass it through the 10 mega ohm input resistor for the voltage stage. And then we just use the voltage measurement front end to measure the voltage, and this separate area, bit of circuitry, to supply the current. To measure this current coming out, we'll use a simple shunt resistor, and in a different configuration, that might be about it. But we have this problem where this V+ source is sitting at somewhere around 10 volts above ground, well outside the range of the ADC. Why it's so high we'll get into later with input protection, but it's because of this mystery box. Blame the mystery box. The simplest way to do this would be to use some voltage dividers. We divide down the 2 voltages here and here and measure them with 2 ADC channels and calculate the voltage drop from there. That could work, but we'd be losing a lot of resolution measuring both of these relative to ground. We may need close to a 10-to-1 attenuation in these dividers to read these in with the range of our ADC, which means we're also dropping our measurement resolution by a factor of 10, and introducing 2 new voltage dividers that can add drift and inaccuracy. Figured there must be a better way. Where I went from here was a sort of co-design between math and the circuit itself. We're basically trying to get a number from one place to another, a current through this resistor up here to a voltage down here across this ADC. And sometimes it can be helpful to just play with some equations and then correlate those 2 circuits rather than just the other way around. That current we want can be turned into a voltage, Vs, by multiplying it by the resistance. And we can have this number scaled up or down before going to the ADC. As long as that scaling is constant, we can reverse it in software. So we'll write that out as an equation, that VADC, the voltage from the ADC input to ground, equals some scaling factor times the current that we want times the resistance. If we think now in terms of equations, what makes a voltage? Well, a resistor with current passing through it makes a voltage. So if we fill in the first part of this mystery box by putting in a resistor, which I'm calling RL since it's on the low side of the circuit across the ADC input, then we make another mystery box that passes a current out of it, IL here, that is proportional to Vs, then we'll get what we want. Rearranging this equation a little bit here gives us a similar looking equation, and it might seem a little obfuscated that we've put Y in here when we could just cancel out RL and get our previous equation back, but it should make sense in a second. So to fill in the next mystery box, we can think again. We've got a voltage coming in and a current coming out, and what component satisfies that equation? Surprise, it's the resistor again. We can deduce that there should probably be a resistor inside this mystery box, and the math says that if we put the same voltage as Vs across that resistor, which I'm going to call RH since it's on the high side, and then direct that current into IL, we'll have a working circuit. So we can fill in RH and yet another mystery box, this time with the rule that it allows IL to flow through it without adding or removing any current, but it drops whatever voltage is necessary to keep this node at the same voltage as this node,
which will keep Vs equal to Vh, the voltage across the shunt equal to the voltage across our new high side resistor. So again, we've got a sort of abstract mathematical definition of two aspects of the behavior of this box that we need. Something that will keep these two nodes at the same voltage without drawing any current from them, and something that will change the resistance between these two nodes to maintain that equilibrium. Well, that sounds a whole lot like an op-amp, which maintains two nodes at the same voltage, and a FET that changes resistance. And conveniently, if we just kind of plop these in here, with the FET source and drain passing IL, and the op-amp with its non-inverting input going to the negative side of Vs, and the inverting input going to the negative side of Vh, and then we connect the two remaining nodes, the op-amp output and the FET gate, it just kind of works. The op-amp will control this FET to keep these two nodes at the same voltage, which keeps the same voltage across Rs and Rh, which means a current will flow in Rh, which is proportional to the current we're putting out to our resistance we're trying to measure, which means that a current will flow through Rh into RL, which will turn back into a voltage, which we can measure with our ADC. Simple. Yeah, this took a while to figure out as the solution that I'm going to use. And this is it. This is exactly how we measure the current that's being sourced by the meter. And with that, we can plug that circuit back into our higher level diagram. This is the circuit we just made, sourcing current through our unknown resistance, and then tapping off here to measure voltage. These two are protection resistors, and this is just a simplified version of our voltage front end. And this works. This will measure an unknown resistance. We just run into the problem again of those 7 orders of magnitude we have to cover. We have to source and be able to measure down to microamps all the way up to potentially a couple of milliamps to get accurate readings at lower resistances. So we want to change out this shunt resistor. And we can do that in a relatively similar way to what we did with our voltage front end, where we just have a couple of different resistors and switches on each of those before going off to that measurement circuit we just built. Conveniently, for once, with these, we are not measuring them bidirectionally. These don't have to take positive and negative voltages across them. We're always sourcing a positive voltage from this side and then currents flowing down through here. So these can be even a little bit simpler. They can just be some P-FETs. Arranged like this, we have some BJTs down here on the low side, which pulls the gates down, which turns them on. And then a pull-up resistor here will turn them off when they're not in use. We do add the on resistance of these FETs to the shunt resistor here. So if these were fairly high and the shunt resistance was fairly low, we could get inaccuracies there and drift over temperature particularly. But these are somewhere below an ohm typically for the components we're using, and these are several hundred, if not several thousand ohms. So the change in resistance of this FET is very small relative to it, so it works out just fine. And that is how we do ranging. That, conveniently for once, is pretty simple. The current input protection is fine for current, okay, but not very good on volts, and does not work at all on ohms. This was a bad idea and it goes in the bad idea drawer. I mean, actually it wasn't terrible, and if you look at it sort of upside down and sideways at the same time and squint and imagine a completely different protection circuit, this does vaguely do a similar thing to a much better plan, in that we've got a transistor being turned off by reverse biasing a diode that controls it, but that's kind of beside the point. I will start with, this thing is not designed, rated, or intended to be used with mains voltage. This had no serious design analysis or testing, or given any indication that it won't try to kill you if you look at it funny. If you build one of these, don't plug it into the wall or use it with mains. Use of this meter may cause burning, itching, or stubbed toes. Talk to your doctor if you experience headaches or loss of smell. Do not look into the operational end of the device. With all of that out of the way, the initial design I was targeting was testing this with 120 volt AC, so I could start moving towards design of something that would work for mains. Again, the current circuitry, not good for it. It is not tested. I didn't design for higher voltage than 120 volt because that's what I work with, and this only has 3 ranges, all the way down to 1.5 volt. So I didn't want to lose precision in ranges I do want, just to have a range that it would never use. As such, it has some protection measures that should, in theory, allow it to measure household voltage without exploding, though I wouldn't trust it with anything. We'll start with current, again, because it's relatively simple. The main thing we have to worry about is overcurrent transients in the kiloamp range. With a normal glass fuse, these could strike an arc as the fuse blows, cause the fuse body to explode, releasing that arc into the body of the meter, then through the body of the meter, then through the body of the user. This is really dangerous. An arc flash can burn or kill you in milliseconds, even if the fuse trips. It works sort of like a Jacob's ladder. The overcurrent starts conducting through the meter like normal, then the fuse trips, and as the metal melts apart, it draws an arc with it. Since there's high current flowing through that arc, it stays conductive long after the voltage normally wouldn't be enough to jump the gap. Since the arc is conductive, but not perfectly, it can dissipate thousands or even potentially millions of watts in the right conditions for a fraction of a second, which effectively explodes. This can also happen at the probe tip. If the meter shorts out completely, or has an arc inside of it, then the noise might make the person holding it start to pull the probes away, which can start to draw an arc off of whatever it's connected to, a bit like a welder, but way more power, and can have the same effect. It explodes in an arc flash, but without even the containment of the meter body. The way to deal with this can be relatively simple at a high level, though there's details I'm sure I don't know. The core of the solution is a high rupture capacity fuse. In really solid meter, these will be big fiber reinforced steels that can contain a nuclear blast or handle tens of kiloamps, tens of thousands of amps flowing through them for a few milliseconds to blow them, and then they will keep everything contained and snuff out the arc. They're usually filled with something resembling sand, so as the metal melts and it retracts, the gap fills up and there's no air gap for the arc to jump through. I used some smaller ones. They are rated for a similar braking current, well into the tens of kiloamps, though I wouldn't trust them with nearly as much, and they're rated for a slightly lower voltage, 400 instead of 1000 for a more standard meter fuse. This is important. We're likely going to blow the fuse in the case of a transient, which is exactly where the voltage is higher than normal. Again, I'm not really intending this to be like used for rewiring an industrial breaker panel, so I'm okay with this limitation. Again, don't use this thing for anything with serious power. In future, I might upgrade these to some more serious fuses, but these are big and expensive, and this thing is already more than enough of both of those. Okay, so other than the fuse blowing to keep everything from exploding, we'd also like the circuitry inside to survive a small overcurrent, a few tens of amps on the milliamp range or a couple hundred on the 10 amp range, without permanent damage other than blowing the fuse. If we look at the circuits, the main danger to this is that the voltage can go across the shunts. There's 2 failure modes here. One's that we put too much current through the microamp range. It won't blow the fuse since it's rated for about half an amp, but we can dissipate a lot of current. And so for this 100 ohm resistor, quite a bit of power, somewhere around 10 watts in our little 1206 resistor. This will absolutely fry it in no time, probably even desolder it from the board. So what we need here is something that can go in parallel with this, that will pass current, or effectively no current at low voltage, but above 1 or 200 millivolts, which is our burden voltage, it'll start to conduct, and it will conduct very strongly before, say, a volt. Now, you don't often see low voltage and low current characteristics of a diode in the data sheet. They will usually tell you the reverse leakage at high voltage and a forward voltage at significant currents, say a milliamp and above. However, a normal silicon diode will have a logarithmically decreasing current over voltage. Our scale here is log current versus voltage, from a volt down to 0. And this decreases towards nanoamp, or usually below, by about 100 millivolts, and will conduct amps or tens of amps by the time you're pushing a full volt through it. So we can just connect a pair of diodes, reversed and in parallel, across our shunt resistor. This will keep more than a couple hundred millivolt from appearing across it, saving it from heating up in an overcurrent situation, and helping limit the overvoltage that could show up downstream. In fact, we do this for all of our shunts. Now we can get away with a single diode here because we've got such a low burden voltage, around 100 millivolts. But if it were higher, or we want even lower leakage, we can connect a couple of diodes in series both ways. And there's some clever arrangements there. So that there's a lower voltage across each of them. So either the same leakage at a higher burden voltage or less leakage at the same voltage. The second failure mode we have is downstream. If there's a high voltage across these, even with the diodes, that will feed into the ADC. For that, we just have a current limiting resistor. We're never going to see like hundreds of volts here for any appreciable time, so it doesn't have to be huge. 1K should probably be fine. And then a low voltage MOV to clamp the voltage to a manageable level, and then another resistor before going into the ADC. And we can just rely on the internal ESD protection diodes at this point. If you're unfamiliar, an MOV acts a bit like we just described with the diodes, but with an even steeper curve and at much higher voltages. It conducts very little current, usually sub-nanoamp, up to some voltage, then trips and conducts very strongly above that voltage, though it still drops that voltage across it. This particular one is rated for 3.3 volts, but it will actually turn on somewhere around 5 volts, and with significant current might allow up to 8 volts across it. So in a significant overload, this point might get up to about 8 volt, but through a 1K resistor, that's only 6 or 7 milliamps once it gets to the ADC diode, which should be okay. And that's about it for current. This is supposed to be the simple one. In a coming video, I'll put my money where my mouth is and test all of this and almost certainly redesign some parts of it in the process. The voltage input protection is next, and it has a couple of requirements. In the current design, it can only measure 120 volt AC, so up to about 170 volts peak. But in the next design, I'm going a bit higher, targeting something resembling a Cat3 600 volt rating, which is sort of the minimum you'd want for any serious meter. Though again, this is not rated and should not be used on mains, period. This is more of an exploration of how to do this on my end than anything else. In any case, if we aim for Cat3 600 volt, that means tolerating 600 volt RMS continuously and 6,000 volt transients without exploding in the user's face or causing an arc flash. Also, this transient rises to 6 kilovolts in just 1.25 microseconds and then holds for 50 microseconds. That might not seem like a huge deal until we remember that capacitors pass current based on the change in voltage over time, and more voltage in less time means more current. We want to limit the current going through the front end during an overload, so we have to have our filtering before we hit that capacitive divider, as in a fast transient, it will have a relatively low impedance. The first stage we saw earlier in the analog front end design, a resistor into an MOV. Recall that an MOV will block current flow at low voltage, but conduct strongly above some voltage. Here we're shooting for around 1,000 volts. This first resistor here is critical to the safe functioning in an overload. If we've got, say, a 1 kilovolt MOV, this must withstand 5 kilovolts across it for a few microseconds, limiting the maximum current that passes through the MOV and thus the energy dissipated in the meter and preventing arc flash. If we didn't limit the maximum voltage with an MOV, then even low current but high voltage transients could arc in later stages and blow up something downstream, shorting the meter inputs across the rail and blowing everything up. If we put the MOV straight across the input, it could shunt thousands of amps once we get above its nominal voltage. That we can still create an arc at the probe and draw thousands of amps at thousands of volts, meaning megawatts dissipated within the meter, pushing everything beyond its energy limits and exploding within milliseconds. So we have to have this sort of middle range impedance to ground where we're dissipating a normal number of amps, somewhere around say 5 to 10 in an overload condition. That puts this first resistor somewhere in the neighborhood of 1K. And this isn't super optimized, so we'll just go with 1K. If that ends up being a problem, we'll change it later. Okay, so this stage sort of suppresses arc flash effectively, limits the voltage going to the next stage, and knocks down some of the sharp edges for really fast transients. Remember that an MOV has a capacitance, effective parasitic capacitance across it. Some quick math, though, will show that it's still an order of magnitude too slow to do much of anything as far as keeping that 1 kilovolt per 1.25 microseconds, or about 5 gigavolts per second edge, from getting through these caps into the ICs. The next stage, with a 100K resistor followed by a 200-ish puff cap, does a much better job there. With the time constant of about 20 microseconds, that suppresses the edge by an order of magnitude. So to somewhere in the range of 250 megavolts per second. Still a lot, but not as bad. We've also got a gas discharge tube here. I've yet to test if we really need this, but this provides some additional protection for everything downstream. It works similarly to an MOV, but instead of keeping its standoff voltage across it, about 1,000 volts, it crowbars the voltage to almost zero, just a few volts or tens of volts, even at very high currents. If you're unfamiliar with the term crowbar, it refers to a literal crowbar. If you've dropped the crowbar across two conductors, it would effectively short them out, even at very high currents, and we're doing something similar-ish here. If overloaded, this will effectively short itself out, kind of like a reverse fuse. It closes instead of opening. In some ways, it's sort of a controlled arc flash, so we can't have it right at the input, but used properly, it can contain the overload to this upstream part of the front end here almost entirely. It is also a bit slower than an MOV, so that fast transient will sort of skip past it at first, but it will help within a microsecond or two and clamp the voltage to something we can tolerate continuously. Doing some quick math to check we're not going to kerplode this input resistor too bad, we can calculate that in an overload it will take as much as about 25 kilowatts, which would cause some problems real fast, but fortunately our transient is faster, ending in just 50 microseconds. So we're only actually putting about 1.25 joules total into this resistor. A joule is a watt second, so heating here will be equivalent to dissipating 1.25 watts for 1 second. So no problem as far as overheating, just as long as this is a pulse-rated resistor. To dive a little more in depth on the differences between an MOV and a GDT, gas discharge tube, we'll show some graphs for each of them. It doesn't completely clear it up, but we'll try to explain it as quickly as possible. An MOV is best described by a transfer function. For any voltage you might put across it, you can effectively look up a current in this chart and see how much it will allow to pass through it. Effectively, it passes little current up to some voltage, and then it starts to allow a lot of current flow above that point in positive or negative direction. The second you drop the voltage below that point, it turns right back off as well. So if you bring a 1,000 volt MOV up to 1,500 volts, it'll conduct like 1,000 amps. And if you drop it back down to 800 volts, it'll turn back off instantly. A GDT is better explained in the time domain. Here we've got a chart of both voltage, shown in black, and current, shown in red, over time. At lower voltages, as the voltage is rising here, it acts like an open circuit, very little current, and much like an MOV, and it has a trigger voltage, called spark over in a GDT, where it starts to conduct weakly, medium voltage and low current. A few tens of milliamps maybe for a short time, called a glow, because the GDT literally glows as the gas inside turns to a plasma. If the source impedance is very high, enough so that the voltage drops below maybe 50 or 60 volts, under a 10-ish milliamp load, then the GDT can stay here or even extinguish, go back to non-conducting. If the impedance is a little lower though, the voltage source can supply significant current, then the arc strikes and the GDT becomes something close to a short circuit, passing a very high current with very little voltage drop. Even though the voltage across the GDT is low at this point, this condition will persist as long as current is supplied. It's only once the supply shuts off, or the transient ends, and we stop pushing current through the GDT that it returns to high impedance. So, after the GDT, our transient gets to this part. The 10 meg resistor should be fine, as long as it can withstand the kilovolt or so that might be across it after the MOV, which we'll design it to be able to, most notably making it out of a couple separate resistors in series. You'll often see this in multimeters. Power dissipated is small enough that it'll probably be fine continuous and easily for a short transient. The capacitor here is a little different. It'll pass a whole lot more power when a sharp edge is present. The filtering we're doing in the front here, combined with the low pass effect of this 330K resistor in series, is enough to keep it from passing more than a few milliamp though. And even then, only for a couple microseconds before the cap charges fully and the current drops. That couple milliamp can get taken up by a couple of active parts downstream, so we should be fine. The first and strangest of these, though, is whatever the heck is going on here. This is a type of protection circuit I've only ever seen specifically in multimeter input protection. It turns out that a couple of regular old BJTs in this configuration will act much like a low voltage MOV, but very fast with very low capacitance and very low leakage. My quick measurements with a couple of 3904s were well into the picoamps at a couple of volts, and I don't trust my measurements below a few nanoamps, so we'll round down to 0. They don't have a particularly sharp turn-on or well-controlled turn-on voltage. They might vary by a couple of volts from batch to batch or manufacturer to manufacturer, or depending on the current we're passing, but will generally be somewhere from 5 to 10 volts. I've still yet to test if these are even necessary in this design, but they'll definitely clamp and absorb any little transients that make it through to here. Finally, we can just rely on the ESD diodes in just about any modern part to handle the couple of milliamp that might make it past all of this. Again, we're dealing with overloads here. Our measurements are already off, so we don't need to worry about performance, just survival without damage. There are 3 main aspects to the resistance measurement front-end protection. There's a resistor and PTC up front, then an MOV, then a diode, and our final mystery box. I didn't include a PTC in the current version because I couldn't find any good ones. For some reason, even the protection ones are grouped together with the sensors on DigiKey. Weird, but the main part of ohms protection circuits in most multimeters is a PTC right near the front. PTC stands for positive temperature coefficient and refers to that as the temperature of this part increases, its resistance also increases, hence it being a positive coefficient. Some materials can have a negative temperature coefficient, so as they're heated, they actually get more conductive instead of more resistive. There's a few different things that are referred to as PTCs. Some are used as temperature sensors, which are intended to have a very linear relationship between the temperature and the resistance. So if we measure this resistance, we can infer the temperature of the part. The type of PTC we have here is more specialized for circuit protection. Instead of being approximately a straight line, we want them to stay about the same up to some threshold, then shoot off to infinity above that. The type we're using will go from somewhere in the range of 200 to 1000 ohms from room temperature up to 70 or 100 degrees C or so, and then suddenly jump up into mega ohms within 30 or 40 degrees. In the plot here, resistance is a logarithmic axis. This rises really fast. We call the temperature where they start to take off the Curie temperature. To first order on all of this, often their stability below the Curie temperature is poor. They might vary by as much as half or double their given resistance. So for a 1000 ohm part, this might vary anywhere between, say, 500 to 2000 ohms over temperature before hitting this point. But we can design around this. Since we're just interested in the current flowing through and it's measured upstream, this changing only changes the voltage drop by it, which we don't really care about that much. Now you might be thinking, what does temperature have to do with this? And really nothing. It's just a convenient way to get a robust component, like a PTC, to change resistance dramatically during an overload. In theory, you could do something with transistors or something else. During an overload, current flows through this front end into the MOV and back out, so any voltage above the MOV voltage gets dropped by the PTC, and that can put a lot of power through it very quickly, and dissipating power in a part makes it heat up, so this heats up, at some point resistance shoots up, drops the current, and so drops the heating, and it will eventually equalize to some tolerable amount of power. Well, we do still have to deal with the MOV voltage. We don't want this whole circuit to kick in at lowish voltages. Otherwise, this will go off if we forget and put the meter in ohms for a second across any voltage at all, and it will both heavily load the circuit and trigger the PTC. So the MOV should be at least a couple of hundred volts or so. So this last part of the front end needs to just handle that. Now for positive voltage, this is easy. We want current to flow out, but not in, and we know a guy for that. A simple diode has got this handled. For a meter like this, though, we also have to deal with negative voltage, and that gets more complicated, hence the final mystery box. The existing design has one of these, but it's bad and does not work, so we won't talk about that. So this mystery box has to allow current to pass through it in one direction, but if we try to pull the output of it much below ground to a high negative voltage, it'll keep the upstream side above ground. Well, we can start with the most basic part here. We know we'll have to have a low resistance under some conditions and a high resistance under others, so some kind of transistor. We'll have to have high impedance to a negative voltage, which means a PNP or a P-channel FET. For this particular circuit, we'll use a PNP BJT. So we'll put that on the low side of the sense resistor in our ohms ranging circuit. Note that I'm not showing all the range switching and measurement stuff here. For the purposes of this circuit, we're only interested in that this node has a resistor pulling it to V+. We don't really care about the rest. Now, we know that all the current coming out of our sense resistor needs to go out to the resistor we're measuring. So whatever is biasing this on has to go back through to the output. So we can put a resistor from base to collector to carry that current. Now we just need something else on this base junction, which will turn this off if it starts trying to pull these nodes too low, too much below ground. So we need a part that won't conduct for a positive voltage. If this is above ground, it will just be high impedance. And once these nodes are at a negative voltage, it will conduct strongly. So sort of steal the portion of current from this emitter base diode so the BJT can't turn on. Well, conveniently, that sounds a lot like a diode. Boom. Diode does the job. So under normal circumstances, ignore the red for a second, we're pushing a couple of milliamp through RS. So this node is a couple of volts above ground. Some of the current, a couple dozen microamps, flows through the emitter diode, turning on the BJT. The diode is reverse biased, so it all flows through this resistor to the output. And since the transistor is turned on by that current, the rest goes through the collector to emitter path. We do lose about a diode drop plus a little bit of voltage, but V+ is higher than we need anyway, so that's not a big deal. In a negative overload condition, the output here pulls down hard to a couple hundred volts below ground. That pulls current through this resistor and starts to pull this junction down to and below ground. That starts to turn on this diode, and as it conducts more, it puts sort of a hard limit on this junction at around minus 0.7 volts, minus diode drop, which means that this node, the emitter, is somewhere around ground potential. Since V+ is about 10 volts, through a 1K RS, we'll get around 10 milliamps flowing to the emitter in the worst case. And so most of that will go through the collector and out the input, but with a huge voltage drop across here. I won't go into a ton of detail, but if you look at it for a minute, you can convince yourself that this stabilizes in this condition. Now, the keen observer will know that a BJT typically has a current gain of around 100. So the collector will only allow about 100 times the current going through the emitter-based diode. But these currents here indicate a gain of over 9,000! The very keen observer will know how to achieve that. I've simplified this circuit a little bit, but in reality, we use a Darlington configuration. This trades a little bit more voltage drop in this transistor for a much larger current gain. So this resistor can be a little bit larger, so all the currents flowing during an overload are lower. This is basically the circuit we use. This effectively acts as a Darlington transistor, which is biased on, so about 2 diode drops during normal operation, and a constant current source during overload. Fortunately, BJTs with a couple of 100 volt standoff are maybe surprisingly common and cheap, especially for our case, where they're quite low current and low power. Going much over 300 starts to limit your options though, so we can extend this by just duplicating this stage a couple times in series like this to get close to 1,000 volts of range out of this. And with the connections shown, which are a slight variation on the standard Darlington, we can sort of cascade the base drivers directly, so we don't get the full 2 diode drop penalty per stage. We get it once at the first stage, but from there, we're effectively going through just the emitter base diodes of this side, and then this side is being driven by those. So we typically get somewhere around 2.5 to 3 volts of drop through this whole thing. That's far from nothing, but we've already got some kind of boost circuit to drive V plus here, and it's never putting out a ton of current. So we can just crank that up a couple of volts and we're golden.
That mostly wraps up the theory behind the design of this. We'll look through the actual schematics now. Starting with the main schematic, we've got our 3 main analog front ends: the resistance current source, voltage, and current. Those put out 5 analog signals that feed into the MUX, PGA, and ADC block, and that's all controlled by the microcontroller. And there's a few communications and digital control lines scattered around. There's little to say about the current front end, it's exactly what we drew earlier. Getting into the voltage front end, the first thing one might see is that these pins here are slightly misaligned from the body of this IC. I should fix that. Nice. The second thing that one might notice is the giant red X over 2/3 of this circuit. This is because when I was initially designing this version, I was considering doing either the inverting or the non-inverting version of the front end, but I hadn't tested the inverting version. Even though it's better in just about every way, the non-inverting version is simpler, so I went with that. This wasn't just laziness. With anything like this, there are a million different things that could be done better, and a lot of getting a project like this over the line is just getting something that works well enough. And for this version, I did, so I just went with it. I knew I was going to test the inverting version eventually, so I kept the parts so I didn't have to remake this later, but marked them to be excluded from the board. The non-inverting attenuator is also a little different from what we went through on paper a minute ago. It's got a slightly different configuration of caps and resistors around the MOV and GDT, and this arrangement is worse. The on-paper advantage here is that in an overload we should see much less current through these resistors and the MOV. But everything else is worse. This huge cap will see the entire overload voltage pass basically the entire thing through the following stages and also short out and blow up everything. The variability in the MOV capacitance mean that we can't get accurate low-pass filtering, and there's no filtering whatsoever downstream, so it's really noisy to boot. It's also got only 2 switches, so 3 total ranges, about 1-to-1, 11-to-1, and 147-to-1, so about plus or minus 1.5 volt, 16 volts, and 220 volts maximum. The star of the show here as far as performance is this switch, an NL7WB66, which is one of the first parts I selected for this meter, almost 5 years ago now. The main thing we're looking for here is low leakage without being crazy expensive. Leakage refers to how much current goes through a switch when it's switched off, or is pushed or pulled to or from the rails. Since we've got such a high impedance signal coming in, and even a very small change to that will throw off our reading, we want this leakage as low as possible. Picoamps would be best. Most parts give a specified maximum leakage at high temperature and voltages, but they're often overly generous. A part with 0.1 nanoamps of real-world leakage might specify 100 nanoamps just to be safe, because one outlier at high temperature and voltage might hit 50. And most people aren't selecting for this anyway. Another part, though, might specify 100 nanoamp maximum and then hit 80 nanoamps at ambient temperature and mid-rail, and you can't tell which is which from the datasheet. I didn't have any problems with excessive leakage with this part, though. It worked great. I did do a quick breadboard of this front end before ordering the boards, but I didn't do that much detailed testing, and never will, because 1 week after ordering the board and parts, this particular switch went obsolete. Yay. So another part of version 2 has been finding a replacement for this part. The inverting amplifier has some similar problems to the non-inverting front end. It's also a little different than what I drew earlier. The first is that we have the same capacitor and 100K resistors upstream of the MOV. There's also something experimental in the switching. You'll have to wait for another video testing version 2 of the design to see how this went. This video is already going to be far too long as is. I was planning to see if I could get away with a higher leakage switch here by using a three-way switch, with the normally open side going to the output of the op-amp as in the drawings, and the normally closed side going to signal ground or common. Since the inverting input is on the other side of the range resistors, and the non-inverting input of our op-amp is going to signal ground, then that node should be at ground. So if the switches are also connected to ground, we should have no leakage going through our range resistors, and so no error. And that's what U23 here is doing. It is three-way switches. U21 here is just for switching out the capacitors. Since a cap doesn't pass DC, we don't need to worry about leakage at all, as long as we put the caps on the high impedance side. I was initially worried about having these caps connect to ground when disconnected, as in the switch here, but that didn't end up being a problem. The resistance current sourcing circuit is exactly what we described earlier on the high side. The difference is in the protection circuit, which again does not work and has been thrown in bad idea jail. A small practical concern is that most op-amps, even rail-to-rail op-amps, can't truly operate at their rails. They need a little headroom voltage between their input level and their supply. In this case, we want the non-inverting input to operate all the way to the positive rail, V plus from the drawings, as that's zero current going through the shunt resistor. The way we achieve this headroom is to have V plus a little bit below the power supply going to the op-amp. Here we have 9V5 ohms coming directly off of the output from the boost converter, and that directly feeds our op-amp supply. V plus from the drawings earlier is this rail, which is connected by a diode, so it's a single diode drop below 9V5, which gives us some space from that rail, so the op-amp is happy. There's also a load resistor over here, R43, whose only function is to load this diode a little bit, a milliamp or so we've still got that full drop if nothing else is drawing significant current. Something you may have noticed is that the boost converter is isolated and has the negative side going to common. This is important since our return current will flow to common eventually through the resistor we're testing, and we don't want to load that op-amp that generates common. It's a reference point, but we can't put a ton of current through it from the rails without causing problems. Replacing this with a simpler, non-isolated converter without drawing excess current from common has also been a big challenge in developing version 2. The rest of this circuit is as expected except for protection, where I tried an SSR and some circuitry to turn it off if the input voltage got too negative, but this was a dumb idea and didn't work, and I'm going to stop talking about it now. The PGA and ADC portion is pretty straightforward. The PGA, or programmable gain amplifier, contains a multiplexer to both select which channel we want to send to the ADC and amplify it by a factor of 1, 2, 4, 5, 8, 10, 16, or 32, all controlled by SPI. This is how we select it for measuring voltage, current, or resistance test current. The analog to digital converter used is nominally an MCP3461R, which is 16 bits and 150 kilosamples per second, and has a pretty good built-in reference. It's on a daughter board though, so it could be swapped out in future. The microcontroller also talks to this through SPI, but there's provision for I2C or even UART to talk to other ADCs in the future. Finally, we get to the microcontroller schematic sheet. This is mainly for the microcontroller, Pi's Pico, but is also sort of a catch-all for all the digital stuff and a few other parts. One of the most important of those being the op-amp that creates our common/ground. This is basically what we drew a long time ago with a simple resistor divider and a buffer. To reduce noise, the switching power supply on the Pi Pico is notoriously noisy. This is fed by a linear regulator and isolated with a common mode choke. This block is our Pi Pico. The main things coming out of this are a pair of SPI buses and a UART. One of those SPI buses runs the PGA and ADC. We want to take a lot of samples for things like true RMS and with accurate timing, so we don't want anything else getting in the way. The other SPI bus connects to everything else, mainly a couple of shift registers that control our digital inputs and outputs, most notably the front panel switches, and we'll get to that, but also a couple of other I/O for controlling things like the volt and ohm ranges, boost converter disable, one-wire mux, and input module. This SPI bus also goes to the input module and to the wireless radios. There's two separate footprints for our radios here, one for an NRF24L01 and one for an RFM69 HCW. The chip select lines are shared between the two of them, so only one can be populated at a time. There's also I2C and UART pins going to the RFM69 HCW. Since it's got some pins that are otherwise unused here, we could make another daughter board with the same pin out for a different radio. The Pico's UART goes to this block, which galvanically isolates it and converts it to RS422. Galvanic isolation is really important. We've got a USB port on the display section, and we don't want a computer that plugs into this to catch fire or damage our circuit. So we want all the front-end signals to be isolated from everything else. This could have been done on the USB port itself, but I also wanted the front end to be able to connect over 422 to something else without a display section at all, and without having to worry about grounding either. We could try to isolate the whole microcontroller from the analog front end, but that would mean isolating a couple voltage rails and like 20 different signals, which is just more cost and complexity. Passing the two UART lines in power is relatively easy. U19 is a capacitive isolator. The supplies on either side can be thousands of volts apart, and it will pass our UART signals through no problem. U7 is another DC to DC converter, but this time it takes in and puts out 5 volts. It doesn't change the voltage at all, just isolates it through a transformer. There will be some capacitive coupling in both of these, but I haven't tested or seen any problems so far from that. After we get our UART into the isolated section, we convert it to RS422, which is exactly the same protocol as a standard UART, but it's differential instead of single-ended, so we need 4 wires instead of 2, and the receivers can tolerate significant common mode voltages, so it's extremely robust. This is used all over the place in industry and aerospace, and it'll be more than robust enough for us here. U18 takes our regular UART signals and converts them into RS422. I had also planned to test LVDS instead of 422 for higher throughput, but didn't end up using that. U25 and 24 are an LDO and LVDS driver, respectively. The rest of the circuitry here is just to be able to shut off the 5-volt input if desired. If, for example, this circuit is running on internal battery and we don't want to drain the display battery, especially since this DC to DC isn't super efficient at low current, we can trigger this opto-isolator, which will turn off this PFET and shut off any power coming in. I've never used this since I've put a very small battery in this part and most of the battery in the display, but we have the option. Here we've got some basic power management for our internal battery. Normally our power comes in through the isolated DC to DC, but we can also run off an internal battery connected to J10 and J11 here. The combination of FETs, resistors, and caps means that this battery will nominally be disconnected by Q18, so we should draw no current, or almost no current from it, when fully powered down, even though the battery is still connected to the board. However, if the microcontroller pulls battery EN high, it's just connected to a GPIO, then Q19 and then Q18 turn on, and that keeps the microcontroller powered up as long as that pin is held high. Once it drops low, it'll take a few milliseconds for R49 to discharge C4, and then it will turn itself back off. So, if the meter is idle and on battery for a while, or senses the battery voltage is going too low, then the software will shut itself down to prevent completely discharging, and thus damaging, the battery. Once we're powered up again through the DC to DC, we can reconnect the battery. You'll notice there isn't any way to charge the battery though. This is one of the corners cut just to get something out the door. This was the last part of the circuit I was concerned about, and speccing out and adding a charge IC, even though that's pretty straightforward, was just going to take too much time. During this past Hackaday SuperCon in 2024, though, I wanted to get something working, so I soldered a couple diodes and resistors directly to the USB power coming from the Pi Pico, and was able to charge the battery, though in the jankiest way possible. My battery has some overvoltage protection, so it's not too bad, but I wouldn't recommend it. There's also provision for using one wire to read out some configuration EEPROMs from the different modules, the main board itself for calibration and configuration information, and same for the ADC, and reading out what kind of input module or radio is attached. I haven't implemented the software for any of this yet, though I've only built 2 boards, so there hasn't been much need.
One of the biggest things that can annoy me about open source projects is when whoever made them makes some arbitrary decision about a better way to do something and builds it deep into the project, which makes it impossible to use the project without either spending 6 months basically completely redesigning or reprogramming the thing from the ground up just to make it work the same way every other thing in the industry does, or completely changing your own workflow in a slower, frustrating, and overall worse way, so you curse them every time you want to use it. And then the developer ignores any feedback about that change and instead tries to explain why their way is better and everyone else would understand and agree and that it works better if only they would spend 3 years digging through their entire code base or design and start only worrying about making elegant tools to make elegant tools instead of you doing ridiculous things like using those tools to make other things. So anyway, on a completely unrelated note, I figured that a bunch of rocker switches is better than a rotary range switch, and here's why. I was emotionally hurt by this multimeter in 2014 because it defaults to AC voltage, and I have to push this button anytime I want to use it in DC mode, and that takes 2 seconds every time I turn on the meter, and that was really annoying, and this was my only multimeter for almost a decade. Also, I've had access to a couple of fancy multimeters through work, but could never be bothered to spend 10 minutes to actually read the manual to figure out how to do logging and other fancy stuff. So naturally, I figured that spending 3 years of my spare time and thousands of dollars to make something far less intuitive was the right path forward, and I stand by that. There are 2 main advantages to using rocker switches like this. One is that I can go buy a big sack of them from AliExpress for like $5. I don't have to design a rotary range switchboard or worry about platings or contacts or co-designing electronics in the case or anything like that, and I like not having to design things and think ahead. The second and more relevant is that unlike a major manufacturer, I can put all sorts of high-end or niche features into this without having to worry about interfering with my sales of a more expensive version of the product. So this will probably end up with approximately 10 billion different functions it can do, even though I'll still only ever use 3. And a rotary switch with 10 billion settings might be hard to turn accurately. We could do the approach that literally every single other multimeter in existence takes and use soft keys, but I don't like soft keys because they are soft and squishy and not nice and clicky like these. More so, I'm often in sort of a groove when I'm working, and I like my tools to work with that and not against it. I'll detour a little into a similar concept about modern oscilloscopes, where everything like vertical channel settings, triggering, and everything else is like 3 soft keys deep hidden behind a context menu. The designers do tend to be pretty good about making things as efficient as possible, but they also try very hard to minimize the number of buttons and knobs and switches, so it's still pretty annoying to reconfigure most of the scopes that I've used, especially one with only a single vertical knob for 2 or 4 channels, instead of having separate controls for each one. Back in high school, I had an old 35 megahertz analog CRT scope, and I could reconfigure every possible setting on it in like 5 seconds, because every single control was a separate switch or knob, and I pretty quickly memorized where they all physically were. Even though it didn't have the same depth of functionality as a modern scope, the basic settings it had could be changed almost instantly, and I could tell where everything was set to in a fraction of a second by looking at or even feeling the switch instead of having to remember or read something on a rather crowded screen. The settings also weren't fighting for screen space. Modern scopes have a much bigger screen, but a lot of that is taken up by what was on an older one spread out over the entire front panel. The point is that it reduced my mental load instead of adding to it, and reduced the friction between what I wanted to do and doing it. It was a total joy to use. I miss it now sometimes, even though the scopes I have are ostensibly better in most ways. The same concept applies to multimeters. I want something that exposes all the functionality it has with as little in the way as possible. My platonic ideal of a multimeter would be something like an old school NASA or fighter jet control panel, 1 billion little lights and switches that each mean or do one thing. Most modern UIs, including fighter jets for that matter, aim more to look clean or be minimal rather than minimizing friction. Even on something like a multimeter, the intent is usually to get the job done with as few keys as possible, even at the cost of slightly more inconvenient interaction. Again, I'm not digging at the engineers or UI designers. They've done a great job with what they're prompted with. It will have been some set of trade-offs that were debated and settled upon as the optimal solution to maximize, in the end, profit for the company through some combination of being low cost to produce, looking good, reliability, size, weight, sale price, and user experience. If we look at something like the Fluke 289, which I've used at work, it has a huge number of options and functions, but all behind those soft keys. Even powering it on is a soft key, not the rotary switch. It's often not obvious what to do to get it to do what you want. The point isn't that this is a more intuitive way the first time you pick it up, it's just that it's not any more esoteric for the more advanced functions, and I'd argue even a little bit simpler. Instead of having to push a button that enables or disables auto ranging and then remember what state it's in and then push the ranging switch 4 times to get it into the range I want, and then when I want it to go back around I have to push it 5 more times to get it to cycle all the way around. With this, I just push the ranging switch to manual and then these to what I want. It's really not any more complicated. I do plan to label these at some point too. This is just as it came off the printer. Actually using this thing a little bit in practice over the past few months, it's become really quick and easy to operate, more so than any of the other meters I've used. Also, it doesn't beep at me every time I change functions. It really annoys me when meters do that. I'm the one that turned the rain switch or pushed a button. I know it moved, I felt it, it clicked. That's great feedback, you yelling at me is not. I feel like this rant is getting long. Anyway, the way these work is relatively straightforward. There's a couple of fixed function switches that are connected directly to the hardware. Specifically, this one that enables or disables diode/resistance, so outputs to the front panel. And this one that switches milliamps and microamps. These are usually separate range switches on a multimeter for the same reason. It's just easiest to physically connect or disconnect these rather than having some kind of solid state switching or relay. After those, everything just sets a state in software. They could be reprogrammed and probably will as I keep developing this. There's a couple fixed function switches. This one enables or disables manual ranging, and this one enables displaying more detailed information, any secondary measurements, for example telling you the test current in diode and resistance modes. Finally, the top left switch enables and disables battery power for the front end, allowing it to be powered off to save battery. The rest of the top row is used for setting up the measurement and basically works from right to left. The first switch sets the basic function. Up is volts, down is amps, and center is other. The second switch depends on the mode of the first. For volts and amps, it sets if we're measuring AC, DC, or AC and DC simultaneously. Since this has a graphical display, we can display multiple readings at the same time. We can also measure volts and amps simultaneously. If the first switch is set to other, then this switch sets if we're looking at resistance, diode voltage, or the input module. In this case, that's voltage and current between this pair of XT60 connectors. The next two set the range. Since voltage has only 3 ranges in this revision, only this first switch is used, and this is straightforward: low, middle, and high range. For current, it's similar, but since this switches milliamps and microamps, this only switches between amps and milli or microamps. In resistance, there's 4 ranges, so the same switch sets the first 3, same as voltage, and if it's up, then the final switch sets between the top 2. So range 1, 2, 3, and 4. Finally, the display has only 2 active switches at the moment. This one to power it on, and this one for the backlight. And that's it. It is a little intimidating at first glance, but it's really straightforward if you play with it for a couple of minutes. To be fair, I did design and program it, but I've changed the layout a few times and can get used to it pretty quickly. Now you might be wondering about this switch, why it looks different and why I haven't talked about it. And that is because it does nothing. Right now this has no function. It's a momentary switch and that kind of goes against everything I just talked about,
So I'll probably change this out in the next version, but it's here now and it does nothing.
For right now, the display section is very simple. It's the display itself, a cheap 128 by 64 LCD module, a Pi Pico, two RS-485 transceiver breakout boards, an NRF 24L01, 4 AA batteries, and a diode. This hasn't had much development, or even a proper board, since it's basically just a display in a nice box. I do plan to upgrade this to a board to get the form factor a bit nicer. I'm not super psyched about the switches on the sides here, and assembly is kind of dodgy. I had to pull the reset button off the Pico just because it kept triggering every time I closed this section up. One might notice I said RS-485 transceivers when I said this uses RS-422. 485 is sort of a superset of 422, with the main difference being that it's designed for bidirectional communication over a single twisted pair, instead of separate TX and RX. But just using two separate transceivers, one set to always transmit and the other to always receive, it's perfectly compatible. The main upgrade this needs is power handling. Right now, this has a diode running from the AA batteries to drop the voltage a little to keep it within the Pi Pico's maximum range, which is one of the worst possible ways to do this. We can't use anywhere close to the full battery capacity before it drops below 5 volts and we start having issues. Ideally, this would be a buck boost regulator that operates down to like 3 volts so we can get our full battery capacity. I could maybe run this directly into the Pico and DC to DC, but that may be pushing it. I think the parts are only rated to 5.5 volt, so 6 volt might not be great, and a little more when fully charged may be a real problem. So next step here to making this work much better, I might also drop this to 3 AA's instead of 4 for space. Again, this was just for simplicity. The switches are just power on one and backlight on the other. I like having a non-momentary backlight. I know it drains the battery. I can turn it off when I don't want to use the display anymore. It kind of annoys me to have to push the button every 4 seconds on other multimeters if it's dark. These two aren't even connected right now. I'll probably add more functions here later. The I/O module hasn't had a lot of development yet. I've got a single module here that measures voltage up to about 60 volts and current up to a couple tens of amps through these XT60 connectors. This was just made on some proto board. I do have a board designed to do the same, but I haven't actually had it made yet. The module standard is more interesting to me. I think it's likely this will have another revision, but I'm not even sure what I'd add to it right now. It's got 5 volt and 3.3 volt digital power, and a low noise 3.3 volt supply for analog circuits. There's SPI, I2C, UART, and one-wire digital interfaces, 4 analog inputs, and 4 digital GPIO. The plan is to have some configuration info on a one-wire EEPROM on every module, so you can hot plug a module and have the meter reconfigure and have calibration information for that particular module. Since I've only got this one module made, I haven't implemented that yet, though. Also, for the moment, the I/O isn't even really working. On this board, I needed a few more inputs for these front panel switches, so I had to steal the digital pins from there. It's all on normal 0.1-inch header pins, so a new module can be made quickly on a breadboard or proto board. The idea being to be able to cut down the dev time to interface some specific hardware to this meter. So often I find myself needing to, say, measure the output of an analog pressure sensor and convert the voltage to a pressure, or something like that. With this, I could solder up a little adapter board myself in 10 minutes and plug it in here, and now I've got a portable, dedicated air pressure meter. Far future, I'd like to be able to set up equations in non-volatile memory, so I could even program this to convert, say, PSI, or any other unit, automatically, instead of voltage. It's got some appreciable vertical space to work with, too, for connectors, stacking a couple boards together, heatsink, whatever else. Another module I really want, and part of the inspiration for this project in the first place, was making a little electronic load module with a big high power FET. You wouldn't get much power dissipation in this little package, but it could go up to a couple hundred milliwatt or pulses of much higher power. The meter itself barely needs to supply any power at all to run even a pretty appreciable E-load, so I'm surprised I haven't seen this functionality in anything else. Final little feature with these is an M3 bolt all the way through the module, board, and into the back of the case to keep everything held well together. I don't usually use this. The pins are usually strong enough to hold it in by themselves, but it's there if you know you'll be using the same module for a while or want to be sure that it won't come out.
The case is, of course, 3D printed. I actually finally broke down and bought a Bamboo, the first printer I bought since 2018, mainly for this project. Most of the case isn't anything particularly special, a slightly rounded off box with some tapers in and out to look like more than a brick. The fuse holder and module are essentially just cutouts. Size was set mainly by the fuses and available space. I needed some space on this side for the voltage front end, but wanted to make sure I had enough volume available to do something useful with the module. Little update to these from version 1 was keying them so they can't go in the wrong way. I am thinking about upgrading to some big boy fuses in the future, so I might change the size of these to match, but no solid plan there. I'd like to be able to get this to work with these smaller fuses, both for price and for size. The 440 milliamp fuse will definitely stay smaller. That doesn't need to handle nearly the same overloads. The fuses go in these holes. Right now I use little bits of heat shrink to keep them from moving, but I plan to add some kind of print-in-place spring or something like that to keep it all one part. Inside the meter body, there's some little guides on either end of the fuse to make sure they stay centered and don't get snagged coming out. Those are right here. Joining the top and bottom together, I used a DB9 connector. Some people seem to think these are old just because they associate them with VGA. But while VGA also used a D-sub connector, these are actually both much older and much more common and current. In my day job, I used to work on military satellites, and they still use these all over the place. In those, Mars rovers, and many more of the most high-tech objects ever made. In any industrial context, PLCs, instrumentation, anything like that, you'll almost always find at least a couple of these. While as a standard connector for something like serial, as it's used here, they're more often than not used for older standards like RS-232. They're still manufactured and used in the millions for new equipment. They're dirt cheap, but often virtually bulletproof. I've used these in probably 100 different situations for a decade now and never had a problem. They're available from dozens, probably hundreds of different manufacturers, so I'm not locked into one company's connector ecosystem or have to change it if they cancel that line or something. If they're good enough for NASA, they're good enough for me. The physical connection between the top and bottom is done with some tapered sliders. This is just a friction fit, but holds on remarkably well. By having a large surface area in the geometry we've got here, little force in it can produce a lot of friction and really wedge these two together without any moving mechanism. I might change this to have a bit more of a clip or a detent. I'm not sure if these tapers will wear out or anything and lose this grip, but I'm very happy with how it works right now. I've fidgeted with this a lot and it hasn't really been a problem. These tapers also make sure that the two connectors align as it comes in. Since there's zero clearance on these tapers, they eventually form an interference fit. We can get way closer than we could with any 3D printed clearance fit and without any additional hardware. The top is just a box inside. The battery holder fits down in between those two tapers. Boards go above that and then the screen. The switches sit out to the sides here and have some little recesses to clear them. The bottom has a big, long, flat part that holds the board and guides for the top. And then the front is basically a hollow box that holds all of the switches, the front panel jacks, and the D-sub connector. I mainly did it this way to keep the front as clean as possible, though I'm planning to redesign this completely from the ground up to make it easier to assemble and take apart. Once the switches and D-sub are wired in, this can't ever completely come apart. The front panel jacks have an M3 thread on the back, and some bolts connect them to the main board. These black oxide bolts probably aren't the best for conductivity. I'll probably get some brass bolts for the next one. But again, I had these on hand and wanted to get this working already. If you can't tell, that's a bit of a theme for this revision.
I originally designed this in Solid Edge, the program you see here. They have a free community edition, and that business model is great. CircuitMaker has basically the same model, and I use that for everything for years. Problem is, Solid Edge is absolutely terrible. It is the second worst CAD software I have ever used. It is based loosely on NX, which I used to use at work and found to work reasonably well, though the UI was kind of annoying to do basic things with. Solid Edge took that idea and turned it up to 11. Even something as basic as an extrusion is an esoteric series of pop-ups and dialogues. There's this annoying box on screen at literally all times, and instead of moving parts along their constraints, they just kind of move and break the constraints, and then if you ask if you want to break them and move the thing there, no, I don't. That's why I made the constraint. I will probably literally jump for joy when I can finally delete this software. I put up with it for this project because it was free and no other reason. With FreeCAD 1.0 having come out, I'm finally happy enough with the workflow there to use it for hobby projects like this. I've used it for a couple of random little things, and it being free and open source is good enough for me to use it for something like this.
And that is basically everything about this thing. Oh wait, software exists. I'll do another video on that, eventually. Or maybe I'll do one on this box, which will probably kill me. Stay tuned to find out in another, 6 months.